Team, this is actually the last lesson, lesson 20. Well, this is the last lesson that we went through before the WPR. So let's talk a little bit about it because we didn't really touch on it. So film interference. Film interference is an analysis of the wave interference when light is incident on a thin film. Typically, this is a typical, right here, what you see here is a typical thin film scenario. And I found it from your concept questions. Thin film scenario. I found it in your concept questions on your course website. Now, what's going on here? So basically we have an incident wave coming in. It hits a thin layer, a thin film. This is a thin film, and this is the thickness, right? Thickness. That's a thin film. And then it is refracted, okay? But once it is refracted, because we have another layer right here, it is also now reflected. So now we have two reflected waves. Reflected wave. And this becomes ray 1 and ray 2. Okay, so conceptually speaking, I think this is one of the hardest. But let me tell you like what's important for you to know. Okay, so we first have to identify what is the phase shift of the reflective wave. So phase shift means that was there any actual, we talked about this before. This is the wave. Was there any actual shift once it started getting reflected, moving to another side? So now instead of starting here, you start here, for example. Okay? All right, so the way that we identify that is by, first of all, let me write the question. What is the phase shift? And pay attention to this one. It will serve you well. All right, so we have the index of refraction, which is 1. And then we have another index of refraction after in the thin film, which is oil, and that is 1.4. But right after it passes that thin film, we have another index of refraction, which is also air in this scenario, because it is just like it's air, the thin film, and then another air. Think about it as a bubble, right? Okay, so immediately for the first one, the phase shift, it goes from air to oil, and it goes from low to high. And this low to high means that since it's going from low to high, there's a phase shift of pi. Just remember that. I know, like, you're like, what? Okay, just remember it's from low to high, it is pi. Now, for this second one, it's going from high to low. So now for this second one right here, it's going from oil to air again. But this scenario shows that it's going from high to low. In this scenario, it would be 0. Again, from high to low is 0, from low to high is pi. If you were counter this, and this is not actually air but something bigger, then it would be from low to high, and then you would have pi here and pi here. But you don't. All right? So this is where it comes out, well, what do I have? So because you have incurred a phase shift, and let me write, what do I have? Because you've incurred a phase shift, you have to find out whether you have a constructive or destructive interference. So thinking about it, this is your first scenario, this is your second scenario. In your first scenario, you had pi, or since it is a phase shift, you have lambda over 2, meaning that there was some type of phase shift. But in scenario 2, once you pass the air, you all of a sudden have 0, so there was nothing. So overall, the change in length, the change in phase was lambda over 2 minus 0 equals lambda over 2. You can think of it, this is kind of confusing, but you can think of it, okay, so if this is pi, just think about it as pi. No, this pi, there's a phase shift. There was no phase shift on the second one. If I subtract pi minus 0, I still am left with pi, meaning there is still a shift between one wavelength or one wave and another wave. And because there is that shift, there is destructive interference. Destructive interference. Okay? So what does that mean for us now? Like we're like, there's a lot of meaning in this. Okay, so we have these two equations, right, that you've seen before, and they can be kind of confusing, but it actually it definitely helps us out with something. It helps us out if by any chance the problem in your either examination or required problems asking you, hey, there was destructive interference, but we want to find that this destructive interference, well, the wavelength of the destructive interference. Okay? All right, so like, let's say that they want to find the wavelength of destructive interference. If you are given destructive already, if you are given the destructive interference of the wavelength of the destructive interference and so on and so forth, and they're asking you to change it to constructive, this is your method of finding the constructive interference. Change it. And this, if you're like, hey, we want to just keep it in destructive and we just want you to find the thickness of the film, then this is the equation to use it. Okay? So, again, if it's, like, let's put it another way. If it's constructive and you want to change it to destructive and they're asking you, like, hey, give me the destructive one, then you use this equation to change it. You use this equation to maintain it. Okay? All right. I hope that wasn't too confusing. Now, so let's go and explain this equation a bit. So this is actually T, meaning thickness. And this is, again, integer multiple. It's an integer multiple, just like for the fringes, to find the maximus or the minimus, depending on whether you're doing interference, destructive or constructive interference. Into multiples of the wavelength. Okay? This is the index of refraction. And this is the wavelength. Okay, so this right here, it is basically like, okay, so what exactly am I looking at here? So this is thickness, but not really. So what it's basically saying is that as you're traveling, this is a ray, and it hits the medium. And as it's going through the thin film, it crosses and it hits another medium, and then it is reflected, right? We are making the assumption that instead of going through like this little angle right here and finding D, we are making the assumption, since it is so small, that the actual ray is just doing this. It's going downwards in the film, straight down, and then straight back up. Distance traveled. So this is distance. It traveled, hit the other side of the film, reflected, hit D, and continue going upwards. These two distances create 2D. And this is actually the thickness of the film. This is why we have 2T. It is the distance traveled through that film. And for those of you that had issues with the Expert TA problem 6, that's where it actually stems from. So the distance traveled for problem 6 was actually at an angle. So you needed to find the distance, not the thickness, but the distance here. Because it was, I believe it was like 45 degrees from the actual perpendicular. All right. Now, I explained that. Good stuff. All right, let's go into the problem. 3.67. Only one problem for this one. I think I stood up too much in my soapbox anyway. So it says a transparent film of thickness, thickness 250 nanometers and an index of refraction of 1.4 is surrounded by air. What wavelength in a beam of white light at near normal incidence to the film undergoes destructive interference when reflected? So I did this. Okay, so this is, it's going in, it's surrounded by air, right? But this is the index, or the ray, the incidence ray. It's going in through a thin film with an index of refraction of 1.40. And then, since it says that it is surrounded by air, this part right here is also air as well. And reflected. So, again, it says it undergoes a destructive interference when reflected. Got it. Prove already, I don't have to do any of it. But just in case, just so you understood, let's go through the first one, the first line. So from the first line, it goes from low to high, because from air to the index of refraction of 1.4, that is low to high, meaning that is pi n2 is bigger than n1. And then again it goes from high to low. And that is equal to 0. N3 is less than N2. Therefore, we have a destructive interference, because it is the same example that we were talking about in this one. We have pi over here, so it's destructive. But it is not asking us to change it to constructive interference. Therefore, we can continue using 2t equals m lambda index of refraction of 2. And it's asking us what wavelength in a beam of light. So we have to find the wavelength, because we already have the thickness. And it is just one. We're going through just one maxima. One here. One layer. So it is equal to 7.0 times 10 to the negative 7. 7 meters. because that is the lambda. That is the wavelength. So m equals 1 because we're only going through one film, and it is just going, like it's the immediate one. And if it was 0, it would be just 0, so it wouldn't count. Okay, I think that concludes the incidents, the thin film, what do you call this? Oof, it's been a long day already, guys. The film interference. All right, so we have that, and just remember, for this one, please focus on this part right here. All right? All right, good stuff. Take care.